So now we're going to go ahead and move on to the little bit more complicated part of momentum and impulse, the impulse portion. So impulse is specifically the moments where you have a collision occurring. So if I were to clap my hands, an impulse happens then. If you were to run into a door, walk into a door, hopefully you're not running into a door, but maybe you walk into it, you weren't paying attention. The impulse is that collision occurring. So the actual definition is that is a force applied to an object will cause a change in momentum. Right? So I was moving with a speed, all of a sudden I stopped moving. That is a change in momentum. The formula for force, or for impulse, is force times time. J is our impulse. And if you notice, if you're looking at your notes, impulse has the exact same units as momentum. The F is still the same with units of newtons. It means force. And T is still time. Now, impulse isn't quite this simple. There is a kind of second portion of impulse. We know that impulse is literally a change in momentum. The way this is written out is you'll see this delta P. So remember this delta, that triangle, means change. So if we write it out here, delta P, the formula for P is mass times velocity. And you just plug in change in P means change in M times V. Since mass is constant, the last part is rewritten as M times delta V. So your formula for impulse, the whole thing, is J is equal to M times delta V. This part is the change in impulse, change in momentum portion. And this is the formula we learned earlier. Force times time is also equal to J. And this is how you'll see it in your formula chart. This may seem really tricky, but we're going to get some little tips, little tricks on how to use this formula. So with that in mind, I want you to ground yourself in why all this stuff is important. Impacts always cause a change in momentum. Any sort of crash that occurs will cause momentum to change, and that can be very dangerous. So what a lot of scientists, engineers, and other people have done over time is figured out ways to increase the amount of time a collision occurs in so that they lower the amount of force that is imparted on an object. Because you'll realize if we're coming to a complete stop due to a crash, that impulse will stay the same. But if we increase the amount of time that it occurs, that F number will go down. This literally saves lives. So the reason for airbags they exist is because they increase the amount of time your body is coming to a stop. You crash into them and you feel that cushion of air increasing the amount of time and lowering the amount of force that you are feeling. It is also the reason those cushions and all those crazy stunts in Hollywood exist, or have you ever seen those firefighters? They hold out those giant sheets for people to jump down to if they're in a building that's on fire. That's so that we can catch them and not have them crash into the ground and suffer a dangerous injury. Other thing is, if you ever caught an egg in an egg toss before, you kind of move your hand with it. You're literally lowering the force by changing the amount of time that egg is coming to a stop. And lastly, helmets. So let's check out this quick video.
Last time we looked at how pads use pressure to distribute the force of a blow over a larger area. Well, there's another physics concept at work here called impulse. We can see how it works with a football helmet. You guys want to help me out?
Sure, sir.
Impulse is the force felt during a collision, multiplied by the duration of the collision. In a given collision, the impulse will be the same, but this can happen the hard way or the easy way.
Be careful up there, Mr. Winder.
Don't worry, I've done this a million times. If you'll hand me that melon. If the duration of the impact is short, then the force felt will be large.
Ouch.
Exactly. The impact with the ground happened almost instantaneously, meaning the force was very large, large enough to burst the melon. If you'll hand me that melon and helmet. The foam padding inside the helmet increases the duration of the collision, decreasing the force felt. So the melon's perfectly unharmed.
It's a headbutt with a 15-yard running start. Wow. Right in the...
So, according to the physics principles of pressure and impulse, I should be perfectly safe.
Hopefully you're able to enjoy that kind of cheesy and silly video made by some of the greatest actors in the world, as you could tell. So now we want to kind of get into those tips and tricks I was talking about just before. I was rudely interrupted by my own brain and these stupid bells, right? So, with all that in mind, I want you to focus on the equation first. We're not going to do any math. What we're going to be doing over these next couple problems is figuring out what parts of the equation we use. So, a door slams shut with a 90 Newton force. So we are given a force of 90 newtons. And then we're also given time. So we are given these two parts, right? We are looking for impulse, and we are wondering what two parts of the equation we should be using. So, if we're looking for impulse, that means our J is our unknown. So do we really need this portion in the middle? No, right? So instead, we can basically block this portion out and only use the equation that is necessary to us for this problem, which will be J is equal to F times T. Since we weren't given mass or velocities, we're able to completely ignore that portion of the equation and just use these two parts. Now we're going to try another one. On these questions, see if you can figure it out before I get to the answer. Because if you can, that means that you are pretty much good to go on this practice and will do really well on the homework that is assigned. So, this time we're given the mass of a 10-kilogram child named Jimmy. He comes to a complete stop, which is 0. After moving at a speed of, this is actually 2 meters per second. So that was our initial velocity. If we are looking for impulse, so again, we're looking for our J, what two parts would we use? Well, I see two velocities, so that should fit into our formula pretty easily, right? Because VF minus VI is how we write this part right here. I don't see force or time, so I'm pretty sure we're not using this. And all we have to worry about is J is equal to M times delta V. And now you're easily able to solve this problem. So now we're going to try another one that might be a little bit weirder. Drew experiences an impulse of 1,500 kilograms times meters per second. If we are looking for the change in momentum, what two parts of the equation would you use? So there is no direct change in momentum, right? We don't know directly what that means, but we are given the force, or the impulse. So let's first write that out, right? J is equal to 1,500 meters per second. Some of you might have already figured it out because you took some pretty good notes on the previous stuff. We learned earlier that impulse is the same thing as change in momentum. Change in momentum would be written like this. Which part of this equation would we worry about, and which part can we ignore? Well, we can ignore the ft because we literally learned just the other slide. I even kind of pointed it out. This m times delta v is the exact same thing as delta p. So all we are looking for is j is equal to delta p. So since we have impulse, we already know the change in momentum. It is 1500. Okay, we got one more practice one, which I will do just in a second. So here's our last kind of question that was similar to the previous three that we covered. Let's just jump right into it. A soccer ball experiences a force of 300 newtons over 0.25 seconds. So that is the amount of time that it takes for the soccer ball to experience the force. If we are looking for the change in momentum, what two parts of the equation do you use? So if you recall, I said delta P is either equal to this portion right here, or it's the exact same thing as impulse. So this is kind of a choose your own adventure type of deal. You get to choose how you want to write the equation. You can write it as Ft is equal to J, which I think is the easiest way to think about this problem. Or you can write it as Ft is equal to delta P. Momentum and impulse have the exact same units because they're the same thing. Impulse is really only a change in momentum, whereas momentum can be a separate standalone thing. So J is anytime there is a change. If we're just moving at a constant thing, then it would be simply P, right? But once the change happens, we got J, right? That's all I'm trying to say. So with these past four problems, I just want to do a quick overview of what we just covered that you might want to write down. And by might want to, I mean definitely write this down. So we know J is equal to M times delta V. And we also know it's equal to F times T. That whole formula that you see up there is what you will see in the formula sheet. We also know delta V is equal to VF minus VI. And so our equation becomes J is equal to M times VF minus M times VI, which is equal to F times T. So the three manipulations of this formula is J is equal to M times VF minus M times VI, M times VF minus M times VI is equal to F times T, and J is equal to F times T. Those are literally the only three ways we will use this formula. You will never have a problem where you have all three in one question. Okay? So always cross out one of the two in order to solve these impulse problems. You'll only ever use two parts. Okay? So your goal is to be able to figure out how and when to use those two parts. So let's go ahead and actually get some math practice, right? We've gotten all those tricks, but it's useless if we can't actually do the math. So here we have a 2,000 kilogram truck that tells us the mass is 2,000 kilograms. It is moving at a speed of 15 meters per second when it runs into a brick wall. So its VI is 15. It takes 0.2 seconds for the truck to completely stop. So we got a T of 0.2. And we are looking, and we know that the VF is 0. Because anytime you see stop or the word rest, you have a velocity of 0. So what is the magnitude of the force exerted on the truck during the collision? Let's write our big ol' impulse equation, right? J is equal to F times T, which is equal to M times delta V. It doesn't matter what order you write it in, just as long as you write it down. I notice that I have F, I have M, VI, T, and VF. The only part of this equation that has none of that is the J portion. So our final equation should look like F times T is equal to M times delta V. So let's write this all out and let's plug the numbers in. So F is our unknown. I know my time is 0.2. We also know mass times VF will be 0. So shouldn't have written it like that, but it's whatever. We're erasing this. So that mass is 2,000 times 0 minus 2,000 times VI, which is 15. And my big old head is getting in the way, so goodbye, head. 15 times 2,000 is 30,000, and the force is multiplied by 0.2. Remember, because this was 0, we'll be left with a negative 30,000. Then all we have to do is solve the last portion and divide 0.2, which I'm going to leave as purple because that doesn't hurt my eyes. Oh no, I can't. Whatever. I changed it. It's too late. 30,000 times 0.2 will give us a value of 150,000. The reason I don't need to worry about the negative is because it's only asking for the magnitude, so it doesn't care about the direction. And just to double check that my mental math is good, yay, it is 150,000 newtons. So, we have one final question that I want to go over. Make sure that you pay attention to everything on the screen. So, a net force is applied. It has 50 newtons. And the mass is 20 kilograms. The car is initially at rest, or the cart is initially at rest, so that tells us our VI is 0. And then the final speed is VF. What is the impulse applied? My equation is J is equal to FT times, which is equal to M times delta V. Notice, I don't have any time in this question. So the portion I will cut up is this. And all you'll have to do is plug the numbers in correctly. And we get J is equal to 20 times 3 minus 0, which tells us the impulse is 60. Now, just finish the work, do the DOL, and you'll be good to go.